Hey there, students. In this clip, we're going to be going over two examples on how to find the resultant of vectors using the parallelogram rule. Okay, so let's go ahead and write down the instruction for the notes. So the task is to find the resultant operations of the given vectors geometrically using the parallelogram rule. Then prove that your answer is correct, that your uh, answer is correct arithmetically. Okay? Alright, so it's a two-part process. We're going to find the resultant vector by using geometric means, namely the parallelogram method, and then we're going to prove that our answer is in fact correct, okay, by arithmetic. Alright, so for number one, we're going to be considering the case of we're going to be finding the operation vector p plus vector r. Okay. All right. So these are the vectors that we're working with right here on this given vector. So what I'm going to do is I'm going to translate all of them into coordinate form, and then use that coordinate form to find the um, geometric representation of the vector operation. Okay. So taking a look at all these four vector diagrams, in order to be able to accurately represent them using coordinates, I will have to draw where the origin is, okay, or the tail of the vector. So you see the vector head, that's the tip, and then this is the tail of the vector. So this is the tail of vector P right here. And then let's draw the tail of vector S. That was the tail of vector S right there. And then the tail of vector R, and then the tail of vector Q. Okay. All right. So let's go ahead and find the representation of each vector using a coordinate system. So in order to do that, all we just do is we'll start from the tail and all the way to the tip. All right. Let's start with vector P. All right. So vector P, starting from the tail, you're gonna go 3 units to the right. 1, 2, 3. So we have 3 to the right, and then we're going to go up 1, 2, 3, 4, 5, 6. 3, 6, okay? So these are just like your typical x and y coordinate. The number that comes first is the displacement of the vector in the x direction from the tail, and then the y coordinate is displacement to the tip of the vector in the y direction, okay? Alright, so let's take a look at vector q. We're going to find the coordinate representation of this vector. So starting from the tail, we're going to go towards the tip. We're going to go 1, 2, 3, 3 units to the right. And then to the tip, starting from there, we just go 1 unit up from the tail to the tip. Okay? Now let's take a look at vector r. How do we represent this using coordinates? Starting from the tail, we're going to go 1, 2, 3, 4, 5, 6, 7. 7 units to the right makes positive 7, and then go up 1 unit in the y direction to the tip. So from tail to tip, it's 7 units in the right direction, and then 1 unit up. All right, let's take a look at vector s. This one we go to the left. 1, 2, 3, 4. Since we're going to the left, that's going to be negative 4. Because we know the negative x direction is to the left, and then we're going to go down 1, 2, 2 units to the downwards to the tip, which is negative 2 on the y, because we know the negative y is downwards in your coordinate system. Alright, so these are the coordinate representations of these four vectors. For number one, we're graphing p plus r. So we're going to be graphing vector P and vector R on the same coordinate system by placing the tails together. So in order to do that, we need to find where the best place to put the tail. Since vector P and R are in quadrant 1, we're going to make the sum is going to be in quadrant 1. So we're going to make sure that quadrant 1 is as big as possible. So to compensate for that size, I'm going to shift my coordinate system to the left as much as possible. So let's put my y-axis to the left, and then put my x-axis really low. Okay? Alright, so I'm going to, starting from this origin, I will graph vector P and vector R. Let's start by graphing vector P. Vector P is 3 units to the right and 6 units up. So starting from the origin, we're going to go 1, 2, 3 to the right, and then go up 1, 2, 3, 4, 5, 6. So there goes the tip of vector P. So let's go ahead and draw the vector. So this right here is vector P. Okay? Alright. Now we're going to draw the next vector, but let's label this first so we don't get confused. This is vector P. Now let's go ahead and draw vector R. R is 7 units to the right and 1 unit up. So starting from the same origin, remember the parallelogram method is tail to tail. We have to put the two tails together. We're going to go 1, 2, 3, 4, 5, 6, 7, and then up 1. Alright? So there goes the tip of vector R. Okay, so we'll draw the vector arrow to represent, and this down here is vector R. Okay, so vector R. Alright, so having drawn these two vectors, placing their tails together, we're going to create a parallelogram using the translation of these two vectors, and then the diagonal starting from these two tails to where the two tips meet of our translated vector, that will be the resultant vector, okay? So how do we do this? What we'll do is we're going to take a projection of this vector, we're going to shift it and place it on the tip of vector P, something like this. And then we'll take the projection of this vector and place it on the tip of R, something like that. And then what you basically have is a parallelogram, and this will represent the sum of the two vectors. This diagonal right here is the sum of the two vectors, okay? Alright, so how do we do this manually? So we know that vector R, let's start with vector R. I want to graph vector R on the tip of vector P. I know vector R is 7 units to the right and 1 unit up. So what I'm going to do is I'm going to start from the tip of vector P. I'm going to go to the right 7 units, 1, 2, 3, 4, 5, 6, 7, and I'm going to go up 1 unit right there. Okay, so that will give me the tip of the projection of vector R onto the top of vector P. Okay, so make sure you draw this vector with a dotted line. So to illustrate the difference, I'm going to draw that with a vector with a dotted line to the tip right there, like that. And then next, I'm going to draw vector P on the tip of vector R. Okay, but just by connecting this final side, that should be the projection of the translation of this vector onto the tip of our vector R. Okay, so let's go ahead and draw that. So we're going to have this vector right here. Okay, so this is the parallelogram we're talking about. Now, where is the sum? The sum P plus R is what you get when you start from where the two tails of the vectors are, and then you connect it to where the two tips of the translated vectors meet. All right, and guess what? This vector we just created here, this vector is vector P plus R. Okay, now what is the value of vector P plus R? In order to find the value of vector P plus R, we can just start from the origin to the tip. Okay, so we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 units to the right. Okay, you see it lines up straight down to this. So we're going to have 10 on the x-axis. And then you're going to go up 1, 2, 3, 4, 5, 6, 7. 7 units in the y coordinates. Okay, so vector P plus R is 10 plus 7. So is our result right or wrong? Now let's verify the accuracy of our result numerically. So title this numeric method. Numeric method. We're going to find vector p plus r. We know vector p is 3, comma 6. And then vector r is 7, comma 1. So what do we get when we add these two vectors? Do we get this coordinate as our result? So let's go ahead and add these two vectors and see what our result is. Okay? So p plus r, vector p plus vector r is basically 10, comma 7. So we see that our answer is in fact correct. Okay? All right. All right. Let's go ahead and take a look at question number 2. In question 2, we're going to do the same procedure, but we are going to be dealing with a different set of vectors here. So for number 2, we're going to be geometrically finding out the resultant vector of 2q minus p. Okay? 2q minus p. Alright, so remember from number 1, we're still using the same vectors. That vector q is 3, 1. Okay? So vector q is 3, comma 1. Then what is 2q going to be? 2q is simply, so this implies that 2q is simply what you get when you double the coordinates of vector q. So you double 3, comma 1. So what you do here is you basically distribute this 2 into 3 and 1. Okay? When you do that distribution, your answer is going to be 6, comma 2. Alright, so that's the coordinates for vector 2q, which we're going to be subtracting vector p from. Alright, so vector p, as indicated in number 1, is 3, comma 6. We're going to be adding the opposite of vector q to vector 2q. Okay, so vector p is 3, comma 6. So what is negative p going to be? Well, why are we doing vector negative p? Because we're combining 2q with negative p. So vector negative p is simply what you get when you take the opposite of the coordinate of vector p, which is 3, comma 6. Right, so what we do here, same as we did in vector q when we're finding 2q, we distribute this negative to both of these two coordinates. And that yields negative 3, comma negative 6 for vector negative q. Okay? Alright, so these are the two vectors we're going to be graphing. 2q equals 6, comma 2. And vector negative p is equal to negative 3, comma negative 6. Alright, so we remember that we're doing this because the parallelogram method just simply finds the sum. So we have to incorporate negativity into the coordinates before we sum the vectors. Alright? Okay, so 6, 2, this means you're going to the right and up. You're in quadrant 1 here. This one is negative 3, negative 6. You're going to the left and down. So we're in quadrant 3 here. So our sum will be somewhere between quadrant 1, 4, and 3. Okay, so let's make quadrant 1, 4, and 3 sufficiently large to compensate for where this result is going to be. So I'm going to shift my y-axis to the left, and then position my x-axis somewhere closer to the top because vector p has a pretty big y-axis. Okay. Alright, so positioning like this looks pretty good. So let's go ahead and draw the first one, 2q. So for 2q, what I'm going to do is I'm going to go 6 units to the right, 1, 2, 3, 4, 5, 6, and up to 1, 2. Alright, so that's vector 2q. Let's go ahead and draw the vector in there. So this is vector 2q. Alright, draw it and label it 2q. Alright, what we're going to draw next is a vector negative p starting from the origin. So starting from the origin, we're going to go down 3, 1, 2, 3, and we're going to go, we're going to go to the left 3, because it's negative x, 1, 2, 3, and we're going to go down 6. 1, 2, 3, 4, 5, 6. All right, so there goes the tip of vector negative p. All right, so I'll draw it like this, and there you have a vector negative p. Okay, let's go ahead and label that negative p. All right, now we're going to use the parallelogram rule to create a parallelogram, okay? So using the same approach that we did before, I'm going to take vector 2q and I'm going to graph it on the tip of vector p, okay? And then connect the left side, and that will be my parallelogram. So vector 2q is 6 to the right and 2 units up. So starting from the tip of vector p, I'm going to go 6 to the right. 1, 2, 3, 4, 5, 6, and I'll go up 2, 1, 2. So this is the tip of vector 2q when it's translated to the tip of vector p. Okay, when its tail is in the tip of vector negative p. All right, so let's go ahead and draw that vector, or the translation of vector 2q. Please use a dotted line here because we're just trying to use the parallelogram rule. So you notice the direction of the translation of vector 2q onto the tip of vector negative p. Still preserve the same direction. And then for vector negative p, you notice it's going downwards, right? So when I'm graphing it here, I'll have to preserve the same direction, so it has to go downwards too. All right, so where's the resultant vector? You draw the vector from where the two tails are to where the two tips of the translated vectors are. Okay, so there goes your resultant vector right there. Okay, so that vector we just drew, that is vector, this vector right here is vector 2q minus p. Okay, and vector 2q minus p, what are the coordinates of vector 2q minus p? You're going to go to the right 1, 2, 3. So it's 3 units to the right. And then you're going to go down like 1, 2, 3. And then we're going to go down 1, 2, 3, 4. Go down 4 units. Okay? So actually negative 4 since we're going down. So it's 3 comma negative 4. All right? Okay, now the question is our answer correct? Is 2q minus p 3 comma negative 4? Well, let's do the same process. We're using a different method. Let's do this arithmetically. Verify this using a numeric method and see if our answer is in fact correct. Okay, so let's use a numeric or arithmetic method, numeric method. All right, so what we're computing here is just simply 2q plus, we're going to add negative p to 2q. Okay? All right, so we know 2q is 6 comma 2. And then when we add negative p to that, negative 3 comma negative 6, what do we get? Do we get 3 comma negative 4? That's the question. All right, so let's go ahead and combine these. So that's going to yield, adding the x's, 3, and then 2 minus 6 is negative 4. So this is what 2q minus p is, 3 comma negative 4, and it matches the answer we got with our geometric result using the parallelogram method. So we're confident that our answer is in fact correct. Okay, so there you have it. And thanks so much for taking the time to watch this presentation. Feel free to subscribe to my channel by clicking up here, and please post a comment to tell me what you think about this clip. You can click like to like this video if you liked it. More clips can be found on mathlearnserve.com. Thanks again and have a wonderful day.